I'm Garrett Wilson, and I will be talking about our paper, Multi-Source Deep Domain Adaptation with Weak Supervision for Time Series Sensor Data. Domain adaptation provides a means to reuse data for new problem domains, but most prior domain adaptation methods don't support time series, and those that do lack support for varying amounts of data availability, specifically multiple source domains and weak supervision. Our contributions fill this gap. Time series arise in a variety of real-world problems, such as human activity recognition, sleep stage classification, gesture recognition, speech recognition, medical diagnosis, and mortality prediction. In many cases, labeled data is expensive or infeasible to obtain. That's where domain adaptation comes in. By using domain adaptation, we can reduce the need for labeled data. Domain adaptation does this by reusing labeled data from one domain to create a classifier for a different but related domain. To illustrate where weak supervision comes from and single versus multi-source domain adaptation, we can look at the various data sources we have available. Most prior works focused on a single source domain adaptation. This is the case where you have a single source domain and a single target domain, where the source domain has labeled data, here some accelerometer data with a walk label, and then we have a second person, the target domain, which does not have any labels. We may also have another source person, and this is the case of multi-source domain adaptation, when using data from more than one source domain. Finally, weak supervision is the case where we have some additional information for the target that's not labels, but a weaker form of information, such as label proportions. For example, in activity recognition, it may be easier to obtain self-reported estimates of how many hours a day I cooked, slept, etc., rather than labeling each data instance of these activities. This avoids interrupting the activities to label the data. We can then run all of these various problems represented here through our model, which we call CoDATS, allowing us to train a classifier for the target domain. The goal is for it to work better than if we just trained a model from person 1 or 2 and ran that directly on the target data without any adaptation. By using adaptation here, we can transfer knowledge from these source domains to the target domain. Our proposed method consists of 3 parts. First, an adversarial domain adaptation method capable of supporting multiple source domains. Second, a time series compatible domain adaptation model architecture based on 1D convolutions. Third, a method to make use of weak supervision if it's available. First, we use domain adversarial training. We can run the source domain data through a feature extractor, and then since we have the labels, we can directly train a classifier with those labels. However, since we don't have labels for the target domain, we can't directly train a classifier on it in the usual way. Instead, we train the outputs of the feature extractor between the source domain and the target domain to be similar or invariant, so that they look like they're coming from the same distribution. We can do this with an adversary, which here is the domain classifier. This is similar to the discriminator in GANs. The domain classifier predicts which of the domains the data came from, whether it's from source 1, 2, or the target domain. It's an adversary because we train the domain classifier to correctly predict this domain label, but we simultaneously train the feature extractor to make this adversary wrong. We do this by negating the gradient during backpropagation, so the feature extractor is updated to make the domain classifier incorrect. The goal of this training method is then to make the feature extractor at test time run on the target data, and because the feature extractor makes the features look similar to how they did on the source domain, the task classifier will now hopefully generalize well to the target domain. To support multiple source domains, we use a multinomial domain classifier. In other words, rather than predicting just a source or target, we predict source 1, 2, all the way to in and the target, giving us a total of n+1 domain labels. We propose using this time series compatible network based on 1D convolutions. The feature extractor portion is a fully convolutional network that has previously been successfully used for time series classification and some other transfer learning tasks. A single dense layer and softmax acts as the task classifier. For the domain classifier, we use a multi-layer perceptron. We use this rather than additional convolutions, since following the global average pooling layer, there is no longer any time dimension. Other works have similarly used multiple dense layers for a domain classifier. In this setup, the variable length nature of time series is handled by the global average pooling layer. In the experimental results, we find that this model architecture yields improvements in both accuracy and computational cost when compared with prior works. For the case where we have target domain weak supervision information, we can take advantage of possible class balance differences between the sources and the target. In activity recognition, for example, not everyone performs the same amount of every activity. I may cook more or less than some of you, or I may sleep more or less. Different people tend to do different amounts of different things. That results in a class balance difference between the domains. So in addition to the domain of variance objective from the previous slide, our method will also select parameters that result in predicting the right amount of cooking, sleeping, etc. for the target domain. The true label proportions are represented as P of y, or here shown y true. In other words, what's the probability that we have a sleep label, a cook label, etc. We minimize the KL divergence between this known label distribution for the target domain and the estimated label distribution from the model on the target data. This estimated label distribution is the expectation over the task classifier's label prediction estimated over a mini batch of, say, 64 samples. Note, this regularization only has an effect when the source and target domains have different label proportions. If the distributions are the same, then the prediction on the target will be close to that of the source domain, making this KL divergence term 0. To summarize, to incorporate weak supervision, we add a differentiable regularizer to the training objective, which constrains the space of model parameters to those approximately matching the target domain label proportions. We evaluate on a number of human activity recognition datasets and a gesture recognition dataset. Shown here are the average accuracy and standard deviation over 3 random initializations for each of 10 random adaptation problems in each dataset, adapting from one person to another person. In these single source results, comparing CoDATS with no adaptation, we can see that performing adaptation yields higher accuracy. When comparing CoDATS with the prior works Ardan and Vrata, we can see the large improvements from the proposed model architecture. Interestingly, sometimes performing no adaptation outperforms the prior works, again showing the benefit of the proposed model architecture, which is also used in the no adaptation case. Recall that weak supervision capitalizes on a difference in class balance between the source domains and the target domain. All of these datasets are relatively balanced except for Wisdom AR, which has a very high class imbalance between domains. So on the Wisdom AR dataset, we can see the benefit of weak supervision when comparing CoDATS WS with CoDATS. We observe about a 6% increase in accuracy. The previous slide was all for single source domain adaptation. Now recall our method supports multiple sources, which we test here. Each point is averaged over 3 random subsets of in-source domains for each of 10 random target domains in the dataset. The left side of these plots are for a single source domain, and the right side is for almost as many source domains as available in each dataset. In agreement with the previous slide, no adaptation, shown in green, performs very poorly on the left side of each of these plots, with only a single source domain. We observe improvements with CoDATS, shown in blue, by using additional source domains, but note that the gap between no adaptation and adaptation with CoDATS is greatest when there are relatively few domains. In other words, using unlabeled target data for adaptation has diminishing returns given additional source domains that adequately cover the space of how people perform activities or gestures. The orange curve shows CoDATS WS, which on the balanced datasets, these first three, performs about the same as CoDATS. However, on Wisdom AR, which is the highly imbalanced dataset, it performs quite a bit better across the various numbers of source domains. Overall, we find that CoDATS can yield an improvement by using multiple source domains, and we can obtain further improvements by also using weak supervision. To summarize, in this work, we introduced CoDATS, which improves over prior time series domain adaptation work by making use of data from multiple source domains, using a new domain adaptation model architecture, and including weak supervision. Future work includes extending to support heterogeneous feature sets, developing additional forms of weak supervision relevant for time series, and further model improvements.